Welcome to Engineering Out Loud, the sixth episode of our series from MECHESOL's MESP Engineering Development Program, titled Geometric Dimensioning and Tolerancing. And if you want to learn more, and maybe even apply to this awesome program, just head over to mechesolco.com/CPD. Now, have you ever wondered how engineers make sure that all the parts of a complex machine fit together perfectly? I mean, think about it. A car engine, a robot arm, even a simple door hinge. They all need to work together seamlessly.
Well, that's where GD&T comes in. It's like the secret code that ensures all those parts work together flawlessly.
Okay, so GD&T, or geometric dimensioning and tolerancing, is basically the language engineers use to make sure parts fit and function correctly. But how does it actually work?
You see, GD&T goes beyond basic dimensions, like length,
Width.
and height. It adds a layer of precision by specifying the allowable variations in a part's geometry. Imagine trying to assemble a puzzle where the pieces are slightly off. It just wouldn't work.
That's a great analogy. So instead of just saying a part needs to be 10 centimeters long, GD&T might say it could be 10 centimeters, plus or minus about 1 centimeters. Am I right?
Exactly. And it goes even further than that. GD&T uses symbols to communicate these tolerances. It's a universal language that engineers all over the world can understand.
So it's kind of like emojis for engineers. But seriously, can you give me an example of a situation where GD&T really makes a difference?
Absolutely. Let's say you're designing a critical component for an airplane engine. Even a tiny deviation in the shape of a turbine blade could lead to catastrophic failure. GD&T ensures those blades are manufactured with extreme precision to guarantee the engine's safety and performance. No room for error there.
Wow, that's a high-stakes example. So GD&T is not just about making things fit. It's also about ensuring safety and reliability.
Precisely. And speaking of making sure things are done right, there's a key standard in the world of GD&T called ASME Y14.1.
Ah, yes. ASME Y14.1. I've heard it mentioned. But to be honest, I'm a little fuzzy on what it is exactly. Can you break it down for me?
Think of ASME Y14.1 as the rule book for GD&T. It lays out the rules for how to apply GD&T on engineering drawings and ensures everyone is using the same language. It's like having a universal set of instructions for building with precision. No more misinterpretations or guesswork.
So it's like the sheet music for engineers. Everyone's playing from the same score, so to speak. That makes a lot of sense. And what are some of the main benefits of having this standard?
Well, for starters, it dramatically reduces errors in manufacturing by clearly defining acceptable tolerances. ASME Y14.1 helps manufacturers get it right the first time, saving time and money.
That's huge. Fewer errors mean less waste and lower costs.
You got it. It also promotes consistency and quality. Products made using ASME Y14.1 are more likely to meet quality standards and perform reliably. And since it aligns with international standards, it enables seamless collaboration between engineers worldwide.
So ASME Y14.1 is not just about precision. It's also about efficiency, quality, and global collaboration. That's pretty impressive. But let's get back to those GD&T symbols you mentioned earlier. They look a bit intimidating at first glance, kind of like hieroglyphics. Can you demystify some of them for me?
Of course. Let's start with form tolerances. These control the shape of a single feature on a part. For example, flatness, indicated by two parallel lines, ensures a surface is perfectly flat, like a tabletop.
Okay. So those two parallel lines are telling me that surface needs to be as smooth as a snooker table.
Exactly. Then we have straightness, indicated by a single straight line, which ensures that a line is perfectly straight, like a laser beam. Circularity, represented by a circle, guarantees that a feature is perfectly round. And cylindricity, shown as two concentric circles, ensures that a cylindrical feature is perfectly round and straight along its entire length.
Okay, I'm starting to get the picture. Each symbol represents a specific geometric control. Now, I'm guessing there are a lot more symbols where those came from, right? But before we delve further into those symbols, I want to remind our listeners that if you're looking to level up your engineering game, be sure to check out MECHESOL's MESP Engineering Development Program. You can find out more and apply at mechesolco.com/CPD. We'll be right back after a short break to explore more fascinating aspects of GD&T.
All right, let's move beyond individual features and talk about profile tolerances. These control the overall shape of a feature, like a curve or a complex contour. Imagine the elegant curve of a car's hood, Profile tolerance ensures that curve stays within specified limits, maintaining its aesthetic appeal and aerodynamic function.
So form tolerances are about individual features being perfect, while profile tolerances ensure the whole shave is within the allowed variation.
Precisely. It's like the difference between making sure every brick in a wall is straight and making sure the entire wall itself is perfectly vertical. Both are important for the overall structure.
That makes perfect sense. And what about those orientation and location tolerances? Those sound pretty important for making sure everything lines up correctly.
You're absolutely right. Orientation tolerances control how a feature is positioned relative to another. Think about the hinges on a door. They need to be perfectly perpendicular to the door frame. For the door to open and close smoothly, that's where perpendicularity comes in, ensuring a 90-degree angle between those features.
Right. A wonky door hinge is never a good thing. So perpendicularity keeps things at right angles. What are some other examples of orientation tolerances?
Well, there's angularity, which controls the angle between two features. That might not be 90 degrees. Imagine the angled supports on a bridge. Angularity ensures those supports are positioned at the precise angle required for structural stability.
I see. So angularity makes sure things are at the right angle, even if it's not a right angle.
Exactly. And then there's parallelism, which ensures that two features, like the rails on a train track, are perfectly parallel to each other.
Okay, so we've covered orientation, which is all about angles and relationships between features. What about location tolerances?
Location tolerances are all about positioning a feature relative to a specific reference point, called a datum. Think of a datum as your home base, the anchor point from which all other measurements are taken.
So it's kind of like the "you are here" marker on a map.
That's a great analogy. Now let's say you're designing a car door handle. You want to make sure that handle is positioned in exactly the right spot on the door. A location tolerance-like position would specify a zone around an ideal location where the center of that handle can be located. This ensures that the handle is consistently placed in the same spot on every car door.
That makes a lot of sense. Consistent placement means every car door handle will be in the same easy-to-reach spot. What are some other location tolerances?
There's concentricity, which ensures that the center lines of two cylindrical features are perfectly aligned, like the rings on a target. Imagine a shaft rotating within a bearing. Concentricity ensures smooth and efficient operation by minimizing vibration and wear.
So concentricity is all about keeping things centered and balanced.
Precisely. And then there's symmetry, which guarantees that a feature is symmetrical about a center line. Think about the wings of an airplane. Symmetry ensures they're perfectly balanced for optimal flight performance.
Okay, so we've got position for precise location, concentricity for alignment, and symmetry for balance.
Now, those datums we talked about are crucial because they provide the reference point. For all those location tolerances, there are different types of datums, each serving a specific purpose. A flat plane datum uses a flat surface as the reference, like the bottom of a part. An axis datum uses the center line of a cylindrical feature as the reference, like the axis of a shaft.
So we choose the type of datum that best suits the feature we're trying to control.
Exactly. You pick the datum that makes the most sense for the specific geometric control you need, and sometimes you need multiple datums to fully define a part's geometry, creating a datum system. That's like a 3D map of the part.
Wow. It sounds like datums and datum systems are the foundation of accurate positioning in GD&T.
They are absolutely essential. And to further emphasize their importance, I want to share a story about a time when a poorly defined datum led to a major headache in a manufacturing project I was involved in.
Oh, I love a good engineering story. This sounds intriguing.
We were working on a complex assembly with multiple parts that needed to fit together precisely. We had spent hours carefully defining the GD&T callouts for each part, but we overlooked a crucial detail. The primary datum for the entire assembly was poorly chosen. It was a small, easily deformed feature on one of the parts.
Uh-oh. That doesn't sound good. What happened?
Well, during assembly, we discovered that even though each individual part met its tolerances, the overall assembly was warped and wouldn't function properly.
So even though each piece of the puzzle was perfect on its own, the whole picture wasn't right because of that poorly chosen datum.
Exactly. It was like trying to build a house on a foundation that wasn't level. We had to go back and redesign several parts of the assembly, which caused significant delays and cost overruns.
That's a painful lesson to learn. It really highlights how crucial it is to choose datums carefully and consider their impact on the entire assembly.
Absolutely. That experience taught me the importance of thinking about the big picture. When it comes to GD&T, it's not just about individual features and tolerances. It's about how everything works together as a system.
That's a great point. Now, before we move on to the global aspects of GD&T, I want to remind our listeners that if you're ready to dive deep into the world of engineering and gain valuable skills, check out MECHESOL's MESP Engineering Development Program. Visit mechesolco.com/CPD to learn more and register. To explore how GD&T connects engineers worldwide. So we've covered like all the nuts and bolts of GD&T, from form tolerances to datums and datum systems. It's really amazing how much precision goes into ensuring parts fit and function flawlessly. But let's zoom out a bit. How does GD&T work on a global scale?
Well, that's where the beauty of standardization comes in. ASME Y14.1, the standard we discussed earlier, is designed to be compatible with international standards like ISO 1101, which also focuses on technical drawings. This compatibility is like having a universal language for engineers worldwide.
So no matter where you are in the world, if you understand GD&T, you can understand an engineering drawing from any country that follows these standards. That's pretty amazing.
Precisely. This shared language is essential. In today's globalized world, engineers from different countries can seamlessly collaborate on projects, share designs, and ensure that parts manufactured in different parts of the world will work together perfectly.
It's like having a global team of engineers all speaking the same language, all working together to build incredible things.
Exactly. And this widespread adoption of ASME Y14.1 brings a host of benefits. Interoperability is key. Parts and assemblies from different sources can work together seamlessly. It also promotes compliance and standardization, ensuring companies meet international quality and manufacturing standards. This streamlines global supply chains, making it easier for companies to source parts from diverse suppliers with confidence.
So ASME Y14.1 isn't just about precision. It's about connecting the world through engineering. It's about building a future where complex systems work flawlessly, regardless of where their parts come from. That's a powerful idea.
And let's not forget about innovation. The clear communication and precision offered by ASME Y14.1 allow engineers to push the boundaries of design and manufacturing, leading to more intricate and high-performing products.
It's amazing how a set of standards can actually foster creativity and innovation. It's like giving engineers a powerful tool to turn their ideas into reality.
Exactly. And lastly, for all those aspiring engineers out there, mastering GD&T and ASME Y14.1 is a fantastic way to boost your career prospects. These skills are in high demand across various industries, from aerospace to automotive to medical devices.
So understanding GD&T is not just about knowing symbols. It's about unlocking a world of possibilities in engineering. And speaking of unlocking possibilities, I want to remind our listeners one last time that MECHESOL's MESP Engineering Development Program is a fantastic opportunity to enhance your engineering skills and open doors to exciting career opportunities. Head over to mechesolco.com/CPD to learn more and apply.
As we wrap up this deep dive into GD&T, I want to leave you with a thought-provoking question. Imagine a world without GD&T. How would engineers communicate their design intent with such precision? How would we ensure that the countless parts and components that make up our modern world fit together and function reliably?
It's mind-boggling to think about. It really makes you appreciate how crucial GD&T is to our modern world. It's more than just a set of symbols and rules. It's the foundation for precision, quality, and innovation in engineering.
GD&T ensures that everything, from smartphones to spacecraft, from cars to medical devices, works as intended, making our lives easier, safer, and more connected.
So the next time you marvel at a complex machine or appreciate the seamless functionality of a product, remember the often unsung hero working behind the scenes, GD&T. It truly is the language of precision engineering, shaping the world around us, one perfectly fitting part at a time,